We are going to look at problem 23.39, which deals with a line of charge starting at x is equal to plus x naught and extends to positive infinity. So the linear charge density is lambda is equal to lambda naught x naught divided by x, where lambda naught is a constant. It says determine the electric field at the origin, so down there. Right. What's interesting about this problem, and maybe a little bit different than other ones, is while we do have a continuous charge distribution, we do not have a uniform charge distribution, right? So we see here that lambda actually depends on the x, so it depends on where we are along this line charge. Doesn't really matter. We start out the problem the same by saying, okay, well, we know that means dq is equal to lambda dl. In this case, is along the x-axis, so we can just say lambda dx. And then we know that the electric field is going to be equal to, we can just say that dE is equal to ke dq over r squared. And because this is really just a one-dimensional problem, we can almost immediately tell where the electric field is going to be pointing. If you forget, well, just remember that this here is positively charged, right? There's a positive charge density here, and we know that the electric field is directed in the same direction in which a positive charge would move if placed in that region. So of course, here, if I were to put a positive charge, it's going to be repelled by that positive linear infinity line type thing down there. Hopefully that makes sense. So we know that this is going to be in the negative x hat direction. So we can just take the integral of both sides, and we say that E, which we know to be along the negative x hat direction, is equal to ke. Then we have our integral. Now dq is lambda dx, but we can actually replace lambda with what we know it to be. So we know from the problem that lambda is equal to lambda naught x naught over x, and then we have r squared, and we have dx. Now we have to figure out what r squared is, right? So r is the distance from our point to dq. And we know that dq is just a little segment, right? And we have tons of these little segments that vary with dx. So every dx is a little bit further away. So we might start off with this one and then this one, and we're adding them all up. So the distance from our point to our charge dq, it changes. And we know how it changes, which is, well, it depends on x. So we know it depends on x, so r is equal to x. We can write this out as E is equal to, x goes from x naught to infinity. We have lambda naught x naught dx over, and then we have x, but we also have x squared, because r being the distance from our point to dq is going to be x, and we know that x changes, right? Because we're taking little steps like that, and x varies from x naught to infinity. We write that out nicely, and we get, I should keep the ke lambda naught, which is a constant, x naught, which is a constant, the integral from x naught to infinity of x to the negative 3 dx. So that's what we have here. And if you don't remember, whenever you have an integral of the form x to the power of the n, the answer is going to be x to the n plus 1 divided by n plus 1. Right, so in our case, we have the integral of x to the negative 3. So that's going to be x to the negative 3 plus 1, negative 2 divided by negative 2 is equal to negative 2 divided by, that's not true, is equal to 1 over 2 to the x squared, right? So negative 1 over 2 x squared. We can put that back in here, and we see that E is equal to KE lambda naught x naught times negative 1 over 2x squared. And remember, we do have to evaluate it because we have bounds. So x goes from x naught to infinity. And we know that's going to be equal to KE lambda naught x naught. Now, negative 1 divided by infinity, that's just going to be 0. Negative, and then we have a negative sign here too, negative 1 divided by 2, x naught squared, like this. So that means E is going to be KE lambda naught, and then we have x naught divided by 2x naught squared is equal to KE lambda naught divided by 2x naught, right? So this is our answer, and this is our electric field, and we know that it is pointing in the negative x hat direction. So just want to go over this one more time just to explain what happened, right? So we had a line of charge. It started off at x is equal to 0 and went all the way to x is equal to infinity. We were able to divide this up into little chunks that we called dx. So we divided it up into tons of little chunks, dx. And we knew that we have the relationship here, or dq. So the amount of charge in this little chunk is equal to the charge density times how wide our spacing is. So we were able to put this definition right back into this integral, and from here all we were doing was solving the integral. The one maybe tricky thing is figuring out that, okay, like r is the distance from our point to our dx, right? So here, because we start out here, really our distance is just going to be x away, where x varies from x naught to infinity. Plug all that in, and then we get our electric field equation down here.